I welcome you all for this lecture series on deep learning. In this lecture, we will briefly discuss about what is convolution networks and how it is being used in the deep neural network. Some basic concepts about convolution neural networks, we are going to see to it. A convolution neural network, that is CNN. CNN means convolution neural network, is a type of deep learning model specifically designed for processing data with a grid like structure such as images. Unlike traditional fully connected neural networks, CNNs use convolution layers with the small filters to automatically and efficiently learn spatial features like edges, textures, and patterns directly from raw input data. By combining convolution, nonlinear activation functions like ReLU, pooling, and fully connected layers CNN can capture both local and global patterns, making them highly effective for tasks such as image classification, object detection, and face recognition while keeping the number of parameters manageable. First, what is a CNN? That is convolution neural network. CNN stands for Convolution Neural Network, a type of deep learning model that excels in processing data with a grid like topology such as images. CNNs are highly specialized for visual data. They automatically identify patterns and relationship between pixels, making them extremely effective for image related tasks. These networks are inspired by the structure of the human brain, particularly the visual cortex, and they mimic the way humans identify patterns in visual inputs. And the CNNs are widely used in computer vision, a branch of AI. In image classification, CNNs assign labels like dog or car to entire images. In object detection, they identify and localize multiple objects in a scene. Facial recognition systems use CNNs to verify and identify individuals based on facial features. In this way, it will be helpful for image classification, object detection, and facial recognition. Before going into CNN deeply, first we will see what is the traditional neural network structure. So this traditional neural network consists of input layer, hidden layer, and output layer. The input layer in a neural network accepts the raw features from the data set, which form which is for an image includes the pixel values. The number of neurons in this layer matches the number of input features. And the hidden layer, what it will do is these layers are the core of neural network where calculations happens. These layers apply weights and biases to the input and activation functions such as ReLU, sigmoid, etc. So many activation functions are there to introduce nonlinear transformation to learn complex patterns. And the output layer produces the final prediction. Functions like softmax or sigmoid are applied to convert numerical outputs into probabilities, allowing for classification into different categories. Next, key steps in a neural network. It uses feed forward, loss calculation, and back propagation. Feed forward is the process where data flows from the input layer through hidden layer to the output layer, generating predictions based on current model parameters. And the loss functions measures the error between the predicted output and the actual label using the loss functions like cross entropy or mean square error. These and all we have seen it in our previous lectures. This quantifies how well the network is performing. Next, back propagation method is used to minimize the error by adjusting the network's weights and biases. This is done using gradient descent, which calculates the derivative of loss functions with respect to each parameters to update them efficiently. And this is the single layer and multi-layer perceptron structures. The single layer perceptron uses the input layer, hidden layer, and output layer. If you are passing the pattern to the input layer, and this input layer is connected with the hidden layer, each input layer, the input pattern is associated with the weight value, and here the hidden layer output we are getting it, and then finally we are getting the output by making use of this activation function. And the neurons output, each neuron's output is given by the weighted sum. It is being given by I is equal to 1 to n. How many inputs are using? Layers are wi xi plus b. This is the b is the bias. And applying the activation function. But the function may be anything. Based on the or depending upon the application, we are going to choose the activation function. This is the generalized format. A is equal to f of z. Suppose if I am using the threshold, my weighted sum value is greater than 1, it will be producing output it as 1. If I weighted some value is less than 1, it will be producing minus 1. And this is the multi-layer perceptron. This is the core of this neural network. It consists of input layer, multiple hidden layers, n 1 to n layers, and the output layer. Here, each layer, each input is connected with the weight value. Here, three input means here all three inputs will be connected with the all the hidden layer neurons, and each layer is connected with the associate with the weight value, and the weight updation is done by using this formula. This we have seen it in our previous lecture. And even though it gives us a good output, it will have some limitations also. And what are the limitations? Here, if you are taking number of inputs, if I am taking 64 cross 64 grayscale image, and what is the limitation of this image if I am taking in the feed forward network, that is FMN? Each pixel will be having the value either 0 or 1. 1 means that is 0 means it will be considered as a black, or white means 255. In between 0 and 255, the values or the colors are being given in terms of grayscale value. This is the stage in between. And the channel size, how we have to take is if I am taking 60, I have to take 64 into 64 into 1, and the 4096 values. So these many input nodes we have to use it. And the next layer, if I am going to consider, say for example, this is the first layer, this is the second layer. In the second layer, if I am going to take 500 nodes, what will happen means for this there should be these all these values, 4096 values should be multiplied with 500. So we are going to get 200480000 weight. These many weights we need to have it. And what is the problem of using this many values? We will be facing the scaling problem. Multiple hidden layers multiply the number of weights. And too many weight calculations will be there in the feed forward neural network. And larger space, search space, and so it is able to, this neural network is, the learning will be very much harder, and more training time is required, and also more resources are needed for executing these many functions. So because of this, overfitting may occur. So high risk of overfitting. And also another one more problem of this feed forward network is flattening the problem. That means 2D image is converted into 1D vector in the input layer. And here, what is the drawback is spatial relationship between pixels are lost. And next, if you are taking the color images, each pixel have color images means mainly three colors we are going to consider. RGB, the channel size, how many we have to take? Three channels we have to take. So the input values are 64 into 64 into 3. So 12,288 inputs are required. And the next node, if I am considering 500 nodes, so this value should be multiplied with 500. So I'm going to take, I'm going to get 6144000 weights. So what is the impact of this? It significantly increases the computational load and slows down many calculations, or there means what will happen? Slows down the learning and makes the scaling to larger image impractical. So in order to overcome all those problems, only we are going for the another important technology or technique known as CNN, convolution neural network. This CNNs, or an enhanced version of artificial neural networks, ANNs, designed specifically to work with visual and grid-like data. They are especially suitable for images and videos where spatial structures of data is important. Unlike ANNs, CNNs preserve spatial relationships. One major advantage of CNN is that they automatically detect important features from data and also in eliminating the need for manual feature extractions. And the CNNs were introduced in the year 1980s by On Lee Khan for the that is who first applied them to digital recognition tasks such as reading zip codes from handwritten inputs. Next, the need for CNNs. Traditional ANNs treat all input data equally and do not preserve spatial structures, making them less effective for images where nearby pixels often relate to each other. Next, CNNs overcome this by learning localized patterns like edges and corners using filters, which helps them understand visual context better. Since the same filter is used across entire input image, CNNs required fewer parameters, making the models efficient in terms of memory and computation. CNNs are also robust to small changes in input like rotation or translation, making them more adaptable and accurate for real world images. Next, if you are going into the CNN architecture, the overview of CNN architecture, and a CNN is composed of multiple layers, as like the multi-layer perceptron, and it's stacked together to process data in stages from simple features to complex ones. And the convolution layers apply filters to the input image to detect features like edges and patterns. And the pooling layer reduce the size of the data by summing information that is weighted, some we are going to find out, which helps to reduce computational load and avoid overfitting. The calculations and all will be seeing in the next lecture. And next, the fully connected layer task the higher level features extracted by previous layers and use them to make final decisions about the input, such as classification. Next to the convolution layers, and it uses convolution layers use filters or kernels which slide across the input image to examine small patches of the image. Each filter is trained to detect specific features such as horizontal lines or vertical lines or curves. This helps build an understanding of image's contents. The result of applying a filter is a feature map that shows where particular feature appears in the image. By using multiple convolution layers, CNNs can detect more complex patterns by combining simpler ones identified in earlier layers. Next, how convolution layer works. Think of filters as magnifying glasses that scan over an image to find particular shapes or patterns. Each filter is designed to look for something specific like a corner or edge, and it activates when it detects them pattern. As the filter slides across the image, it lights up when it finds a match, helping the network identify important features. The final output of this process is a feature map which highlights the areas where the pattern was found, guiding the network's focus. Next, the pooling layer. Pooling layers reduce the size of feature maps, which means fewer computations and faster training. And by summarizing the presence of features in an area, pooling allows the network to focus on most important aspects of the images. Pooling also helps avoid overfitting by making the network less sensitive to exact location of features. Maximum pooling selects the largest value in each region, capturing the most prominent features, while pooling takes the mean of the value to give you a smoother output. Next, why we have to use pooling? The pooling is like a simple zooming out and summarizing detailed parts of the image to see bigger picture. It makes the model more robust to small changes like movement or noise in the input image. Pooling significantly reduces memory and processing needs, making the model more efficient. Next, fully connected layers. After feature extraction through convolution and pooling, the data is flattened into a single long vector. Each neuron in the fully connected layer connects to every output from the previous layer, enabling comprehensive decision making. These layers analyze the entire image globally and decide what the extracted features mean in the context of classification tasks. For example, the final fully connected layer might determine whether the feature matches a cat, dog, or bird. Next, feature hierarchy in CNNs. The first layer in CNNs detects simple patterns such as edges or lines from the raw data image. As the data passes through more layers, it captures more detailed features like circles, textures, and repeated patterns. In the final layer, the network is able to detect entire objects like eyes, faces, or cars depending on what it has learned. This hierarchical deduction process helps the CNN understand visual inputs from the simplest to more complex patterns. Next, coming into the applications of CNN. In image classification, CNNs label the entire image with a single category such as dog or aeroplane. In object detection, CNNs not only identify what objects are present but also locate them with the image. In medical imaging, CNNs are used to detect tumors, fractures, or other anomalies like X rays, MRIs, and CT scans. And the CNNs help self driving cars by recognizing traffic signs, pedestrians, and other vehicles to enable safe navigation. Next, face recognition system uses CNNs to authenticate, identities by comparing facial features against known database. CNNs beyond images. CNNs can also be applied to 2D representations of audio data like spectrograms, enabling tasks like speech and music recognition. They are useful in time series data analysis where patterns can be treated similarly to image segments, such as in financial or sensor data. Text data can also be converted to matrix form using embeddings, allowing CNNs to perform tasks like sentiment analysis or a spam detection. Although CNNs work with these type of data, recurrent neural networks (RNNs) and transformers are often more suitable for sequential information due to their ability to handle long term dependencies. Finally, why CNNs? CNNs are among the most efficient and accurate models for solving problems involving visual inputs. They learn hierarchy of features that helps understand images at multiple level details. And with the CNNs, there is no need for manually specifying features as the network learns what's important during training. And CNNs have set benchmarks in numerous applications, including face detection, self-driving cars, and healthcare diagnostics. Coming into the summary, CNNs help computers see by analyzing images much like our eyes and brain do. I'll tell you one more time. CNNs have helped computers see by analyzing images much like our eyes and brain do. They learn patterns from the images, starting from basic lines and moving to more complex features. Each layer in the network builds on the previous one, gradually improving understanding of the image. Pooling acts like a summary step, keeping important information and reducing complexity. Finally, fully connected layers interpret learned features and make decisions about what the images contains. So in the next lecture, we'll take one problem and how the kernels are applied onto the image and how you are getting the output, how that output has been given as input to the layer, fully connected layer. Thank you for attending this session on CNN. I hope you now have clear understanding of how these powerful models functions. The remaining things we'll discuss in the next lecture. Thank you.